ray tracing. So now that we have learned how ray casting works, we can look at ray tracing. So rays are often used to model the light paths in the scene, because light also travels in a straight line in the same medium. So let's say we have this situation. We have a camera, we have a screen, and we have some triangles in our environment. If we want to do ray trace rendering, then we can shoot rays from the camera through our screen or through each of the pixels in our screen. So basically we will do this in the fragment shader, which is run for each of the pixels. And we need to see what scene geometry these rays intersect with. Let's say that this ray hits this triangle. When we have this hit point, we could calculate a lighting model here. We could see how much direct illumination this point gets, what's its color, and we could return that color as the color of that fragment. But we could be a bit more smarter here. Instead of just taking the vector L, we could shoot another ray towards the light source in the direction of L. And if that ray now hits some other scene geometry, then we know that the light is actually blocked. So this is this obstructing triangle, for example, that blocks the light. So this point here doesn't actually receive the light coming from the light source. Now we could also have this surface be reflective. So we create another ray, a reflection ray, at the same angle as the angle of incidence. So now we have this reflection ray. Let's say it hits some other scene geometry. We could calculate the illumination over here. What color should this point on that triangle be? And we can use that result to backtrack along that ray and add it on top of the result from this hit point. So this approach would sample the reflections in the scene. Of course, we could go wild and shoot rays in all sorts of different directions from this hit point, sampling the scene illumination from all around, because physically all of these points could contribute to the illumination of this point. So this would kind of give us this global illumination approach where we sample the scene with rays, and we know that, well, let's say on this ray there is this red light coming in, maybe there's red light coming in from all sorts of these rays, so we need to add a bunch of red light coming in to this point to calculate the final color value. And there are also things called refractions, so some of the materials can be transparent, but with transparent materials the ray doesn't just pass through them in the same direction, but there is this index of refraction. So depending on the material it is, this ray could bend or this angle could change more or less. So let's say this would be a glass triangle. So we would need to sample the scene from behind this triangle at specific angles. So we would shoot these refraction rays to do that. And well, here is an example. So we have this reflective sphere in the middle of this hanger here. Well, this is a very interesting hanger, which we'll look at a bit later. So we have a green wall on the right and a red wall on the left. And on this reflective sphere, you can see that we're getting the reflection of the red wall on the left side of this sphere and the reflection of the green wall on the right side. And this is rendered with ray tracing. Now, ray trace rendering can be quite expensive. So let's say we have a screen with width 800 and height 600, and let's say that we do 3 bounces, or this could be just additional rays that we shoot for every pixel. It could be a shadow ray, could be a reflection ray, maybe we do a refraction ray, or we shoot 3 different rays in different directions, or we do a 3-hop trace. For example, here we don't just stop at the first intersection, but we shoot another ray, because there could be light coming in to this point that is then contributed to that ray as well, and ultimately to the final result. And that would semantically make more sense as this trace, because we're kind of recursively ray tracing the scene and tracing out the light paths that end up in the camera. So let's say that for every ray we shoot 3 more rays, or actually that would be 2 more rays including the ray itself. And let's say that our scene consists of 700 triangles. This is very few. In reality, the scenes are much more complex with a lot more triangles. So now we have this number of rays that we need to calculate every frame, and we need to calculate the intersection tests between all of these rays and all of these triangles. So this is going to be over 1 billion tests every frame. And that is why ray tracing is usually very expensive. So from this video, you should now understand ray trace rendering. So we can trace the direct illumination, we can trace some indirect illumination, we can trace shadows, we can trace reflections and refractions. And you should also understand that ray tracing is quite expensive, because in the naive case we need to test the intersections between every ray and every triangle in the scene.